Okay, so this is part 3 of constant coefficients. This is the part where we're going to solve higher order differential equations with the constant coefficients. Of course, they're still homogeneous, as we can see right here. Now, we're still going to use the same substitution. We're going to assume that y equals e to the rx is our solution. When we plug it in, we will get a n r to the nth power plus a n minus 1 to the r n minus 1 plus a naught plus equals 0. And so we'll basically just have a higher degree polynomial to solve. So what we're going to do is look at the different cases. So our case 1 is if we have all the roots R1, R2 to Rn, there would be an n of them. They are real and distinct. This is exactly like our case 2 up when we were just using the second degree or quadratic. Okay, then our solutions are e to the r1x, e to the r2x, e to the rnx. And there's n of them because this is an nth degree. We should have n distinct independent solutions, and because they are all different, they are all independent. So that's our fundamental set. And so our general solution is y equals c1 e to the r1x plus c2 e to the r2x plus cn e to the rnx. Done. Now our case 2, some of the roots have multiplicity k, so they're repeated roots, but they are real. And this is going to be similar to our second case in the quadratic, where we have repeated 2 roots. So what we have to do is we have to multiply them by some power of x to make them independent. So our fundamental set is e to the rx. There's only one r because it's repeated with multiplicity k. And then our second one, just like the second order, x e to the rx. And then our third will have to be the next highest power by another x, e to the rx, all the way to x to the k minus 1, e to the rx. That will be k of them, since we do start here, and so that k to the 0 counts as an extra one. And so our general solution and we will box our solution. Okay, so now let's look at a couple examples. Okay, so here's the third order. So we start off the same way. We see they're all constant coefficients. So we start y equals e to the rx. Y prime, we'll have to go 3 of them. We need the third derivative of this. So we factor out that r to the x. You can just start factoring it out from the beginning, but don't skip writing it all together. Again, it just helps you remember where it comes from. Okay, so now we need to solve this. It looks like we're going to have to use synthetic division. Now, if you remember, you want to use the coefficients. So there's a 1 there. And make sure there's a 0 placeholder if you ever do skip a power. So the coefficients are 1, minus 2, minus 5, plus 6. And again, 3, 2, 1, 0. And remember our possibilities? Possible roots, rational roots. We start with this, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And that's it, because there's a 1 here. If there was a 2 in front of there, I'd have to take all those answers and divide all of them by 2 for an extra set of answers. So, I probably would start in the middle, maybe 2 or 3. We'll start with 2. So you drop the 1. You're always adding down. Okay, 1 plus nothing is 1. And then we multiply these two. This times this is 2. We add down. That's 0. 2 times 0 is 0. Add down. And then 2 times minus 5 is minus 10. Add down. And that is the last one is your remainder. So it looks like that doesn't work. So I'm going to try it again. I don't want to, either I got to check off what I've done or I'll just do it again so I can see what I've done. If you erase it, you might forget what you've done. So we want to try minus 2. Minus 2, so drop down, multiply, minus 2 times 1 is minus 2, minus 4, positive 8, 3, minus 6, and we have a winner. That's my remainder. That means it goes in evenly. So now we want more roots. So this is the polynomial that's left, and this would be x squared, x minus 4x to the x plus 3. I mean, we can stop and factor it if we want, but this will definitely work for one more root, even 2 if you want to go further. So you don't have to rewrite this to see if another one goes through. All we have to do is continue with our polynomial that's right here. That's a second degree now. So I've tried 2, I tried negative 2, I'm going to try 3 now. Okay, so I've tried that. So let's try 3, 1, 3, minus 1. And by the way, our last term here, our new possibilities are plus or minus 1, plus or minus 3. Okay, so we're trying the 3. And then here we have multiplying this times that is minus 3. Oh, we found it. And so our last factor, that's always your constant. When that's your remainder, that's a constant, and that's the next highest. So that's my last factor. My other factors are, this is the root is 3, so x minus 3 is the factor. So it's the opposite, don't forget that. This is the root, these are the roots. It's x equals negative 2 or x plus 2 is the factor, equals 0. And so I factored it. I mean, you don't want to check it, but maybe you do your first time if you forgot this process. So again, that's a third power. We did get 3 solutions. My R1 equals minus 2. The order doesn't matter. My R2 equals 3, and my R3 equals 1. Okay, so again, these are your roots, are negative 2 and 3. I go back. And so these are all different. None of them are repeated. So my fundamental set is e to the minus 2x, e to the 3x, and e to the 1x. So just x. And my solution, C1, e the minus 2x plus c2e. And again, the order does not matter. They're all independent because they're all different roots, which we proved before. Okay, that one wasn't too bad. Let's do another one. So we're going to use y equals same thing. And you might want to do this, or maybe you can skip it. I'd be careful though, down here you can mess up. Plug it in, basically you're going to be factoring that out, and then what'll be left with will just be the y to the third, r to the third. This one has the r squared plus 3r squared left, plus 3r, because the y has the r in it, and the y is just the coefficient that's left because you factored this out. Again, do the steps if you like. It sure does help you not make silly errors when you do all the steps. And now, so let's use synthetic division. And really, our possible roots, or the factors of this, are possible, are plus or minus 1. Since they're all positive, I think it has to be -1, wouldn't you think? If you do all positive, everything will just get bigger. Oops. Let's not make a mistake. So drop down, multiply is -1. That's 2, minus 2. That's 1, which is -1, which is 0. Okay, we got what we wanted. We can go one more time. Add. And to be honest, since we don't really need to factor it, we could even go one more time. It works. Okay, so that means we found our 3 roots. Or you can write them as products and whatnot. So we have r equals -1 with multiplicity of 3. Or r minus 3, r minus 1 to the third equals 0. Just so you can see it. So our fundamental set is e to the minus x is my first r, x e to the minus x is my second r, x squared, make it independent, is my third solution. General solution. Let's do another example. So here we'll get 1r to the third plus 1r squared, r plus 20 equals 0. Plugging it all in and factoring it out. So synthetic division. Okay, so now we have quite a few more choices. We get plus or minus 1, plus or minus 20, plus or minus 2, plus or minus 10, plus or minus 5, plus or minus 4. I'm actually going to start with 2. They're all even. I don't know. Maybe because I know the answer. 3, 6, minus 10, minus 20. Oh, look at that. It works. Okay, let's keep going. So do you think I would have one with 3 distinct roots again? Probably not. I'm going to try 2. Now we have cut down that, the 20, because those are my new possibilities, the last term. But let's try the 2 again. Drop down the 1, multiply 5, drop down the 5 times 2 is 10. Oh, look at that. And then we can kind of see what the last one is. My choice, it's going to be x minus 5. So minus 5 works. That's an x minus 5. So you can see it's x equals 5, actually positive 5. So 1 down. They're both positive. It'd have to be a negative. Times a 5. It'd have to be a negative 5 because they're both positive. 1 down, minus 5, 0. There we go. Be careful with that. Oh, that's x plus 5. Those two. Okay, so, if you want to write it as factors, here's something that can help you to make sure you got the right one on the last one. X minus 2, x minus 2, this is x plus 5 equals 0. So again, remember, it's the opposite. This is the root of x equals 2, which is a factor of x minus 2. When I set this equal to 0, I get the root 2. So now let's look at minus 2 times 5, positive 4 times 5, it's positive 20, just to make sure your signs work out. Kind of a partial check. Okay, so our fundamental set is e to the 2x, x e to the 2x, and e to the minus 5x. So we can have, it doesn't matter the order, you have a multiplicity of 2 here, so we could have a combination of both cases, is my point. Solution, general solution. And that's the end of this problem. Now what we're gonna do, and just a real quick note, we haven't seen it yet, but if r is equal to 0, then you get e to the 0x, which is 1, okay? For example, d to the 4th y dx to the 4th equals 0. So using y equals e to the rx, what happens? So y prime, we want the 4th, y to the 4th. This is r e to the rx, y double prime. It's r to the 3rd. And y to the 4th, which is what this is. So we only have one thing to plug into it. It's r to the 4th e to the rx equals 0. So this can never equal to 0. Therefore, r to the 4th is equal to 0. So it's r equals 0, multiplicity 4. So it's e to the r 0, right? Sorry, e to the 0x, which is just 1. Okay, so so my set, my first one is just 1, times x times 1, times x squared, times x to the 3rd. Okay, that's my solution. That's my that's my fundamental set, and my general solution. And I thought that was a neat one, personally. Okay. Okay, now I'm actually going to cover case 3, complex. Roots are complex but distinct. So definitely we'll be using Euler's formula. And just a note, This is about, you might have learned this in pre-calc, maybe not. If the characteristic equation has real roots, real coefficients, then the conjugate roots must come in pairs. Complex roots come in pairs. It's the conjugate. So let's look at an example. So we're still going to use e to the rx. So each of these we're going to factor out e to the rx. And what's left is r to the fourth plus 13r to the third. Plus, this is the last term, 36y is 36 e to the rx, the e to the rx factored out. Okay. So what we have here is a fourth degree polynomial, three terms suspiciously looks like it could be factored into two binomials, r squared, plus 36, 9, and 4. Oops, that's a 13. I just copied it wrong. Oh yeah, so 9 and 4, if it's plus and plus, oh yeah, that's 13. So r squared plus 9 equals 0. R squared plus 4 equals 0. Square root. R equals plus or minus 3i. And same with this one. They're both complex. Plus or minus. There's our conjugate. 0 plus or minus. 0 minus. 0 plus 2i. 0 minus 2i are conjugates. Write that out a little bit better. Okay, so we have 4 solutions. You always should have 4, even if they're repeated. Get your multiplicities in there. So that way we'll have 4 elements, independent roots in our, 4 independent solutions in our fundamental set. Okay, so you ready? So the nice thing is that alpha is 0 for both. Beta equals 3. Alpha equals 0. Beta equals 2. So let's write our set. Since we don't have, it's e to the 0, which is e to the 1, it's just gone. So it's e to the 3i, e to the minus 3i. Let's start here and then we'll work away. So from these two, remember it's a lot of work. You can actually do it. It's not that hard using Euler's. But if you remember, it's going to be sine and cosine. Alpha is 0. So it's going to be cosine of 3x from those two, comma, sine of 3x is my second independent one from those two. And from 2, it's cosine of 2x, sorry. 2x and sine of 2x. That's my set, changing them to real. And my general solution. Okay, so again, always remember 4th degree, 4 independent solutions, okay? And so if they're, we know what to do with their multiplicities. So that's it for this section, okay?